We now discuss the solution of a problem from the section Linear Algebra. The problem is on the solutions of linear systems. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and this question is from the section C. The given problem is let A be an m by m matrix with real entries, and let X be an m by 1 vector of unknowns. Now consider the two statements given below. Statement 1. There exists a non-zero vector b1 belongs to R power m such that the linear system Ax is equal to b1 has no solution. Statement 2. There exists non-zero vectors b2, b3 belongs to R power m with b2 not equal to c times b3 for any c belongs to the set of real numbers such that the linear systems Ax is equal to b2 and Ax is equal to b3 have solutions. Which of the following statements are true? We are given four options. Option 1. Statement 2 is true whenever A is singular. Option 2. Statement 1 is true whenever A is singular. Option 3. Both statement 1 and statement 2 can be true simultaneously. Option 4. If m is equal to 2, then at least one of the statement 1 and the statement 2 is false. We are given an m by m real matrix capital A. Capital X denotes an m by 1 vector of unknowns. And we are given the following two statements. Statement 1. There exists a non-zero vector b1 belongs to R power m such that the linear system Ax is equal to b1 has no solution. There exists such a b1 belongs to R power m such that Ax is equal to b1 has no solution. You have to remember statements 1 and 2. Statement 2. There exists non-zero vectors b2, b3 belongs to R power m with b2 not equal to c times b3. That means for any c belongs to R, that means b2 and b3 are linearly independent such that the linear systems Ax is equal to b2 and Ax is equal to b3 have solutions. Then you have to discuss which of these following four options are true. Before entering into the discussion of the solution of the problem, we recall the following result from linear algebra theorem. The following statements about a system, linear system Ax is equal to b are equivalent. First statement. Ax is equal to b is consistent. That means Ax is equal to b has a solution. 2. B belongs to column space of A. These two are equivalent. 3. The rank of the augmented matrix A with the column vector B is equal to the rank of the coefficient matrix A. And these three statements about Ax is equal to b are equivalent. 1 implies 2, 2 implies 3, 3 implies back to 1, or any two are equivalent, and all are equivalent. Agreed. We will repeatedly use this theorem in the discussion. Please remember. Now, we go to the option 1. The option 1 is statement 2 is true whenever A is singular. Is it true? Is this statement true? So, we give a counter example like thing, but not exactly. Suppose that A is singular, because A is given to be singular, you take A is singular, but you take let rank of A is equal to 1. So such a singular matrix you take. Agreed? That is, the column rank of A is 1. Column rank and is equal to row rank is equal to rank. Therefore, rank of A is equal to 1 means column rank of A is equal to 1. Assume that the statement 2 is true. That is, there exists non-zero vectors b2, b3 belongs to R power m such that b2 and b3 are linearly independent such that Ax is equal to b2 and Ax is equal to b3 have solutions. And because we have assumed that the statement 2 is true, so there are two linearly independent vectors b2, b3. b2, b3 belongs to the column space of A, and because they are linearly independent, the column space of A has at least two linearly independent vectors. They are linearly independent because b2 is not equal to c times b3 for any c belongs to R. So, the column space of A has at least two linearly independent vectors, means the column rank of A is at least 2. That is, column rank of A is greater than or equal to 2. But the column rank of A, we have 1. And now we got greater than or equal to 2, a contradiction. This contradiction because of our assumption. Therefore, the option 2 is not true. Therefore, the statement 2 is not true when A is singular. Thus, the option 1 is not true. Agreed. We move to the next option. Option 2. Option 2 is statement 1 is true whenever A is singular. We prove this one. A is singular because it is given, implies the rank of A is less than m because A is an m by m matrix. This implies the rank of A is equal to column rank is equal to row rank. That implies column rank of A is less than m. This means the column space of A is a proper subspace of R power m. Therefore, there exists a B belongs to R power m, B not equal to 0, such that B is not an element of column space of A. This is possible. So, this implies there exists a B belongs to R power m, B not equal to 0, such that B does not belong to column space of A. So, recall our earlier theorem. B belongs to the column space of A is equivalent to Ax is equal to B is consistent. Now, B does not belong to column space of A will imply Ax is equal to B is inconsistent. Inconsistent. That means it has no solution. That means the statement 1 is true when capital A, the matrix A is singular. So, thus, the option 2 is true. Move to the next option. Option 3. Both 1 and 2 can be true simultaneously. Here, the meaning is 1 and 2 are true in some context or in some situation, but not always. At least in one situation, it is true. So, suppose the statement 2 is true. Agreed? That means statement 2 is true means there exist non-zero vectors b2, b3 belongs to R power m, where b2, b3 are linearly independent such that Ax is equal to b2 and Ax is equal to b3 have solutions. This means b2, b3 are the solutions. Ax is equal to b2, Ax is equal to b3 has solutions. Now recall the earlier theorem. Then it will say b2, b3 belongs to column space of A. Because b2, b3 are linearly independent, column space of A has two linearly independent vectors. Agreed. So when 2 is true, this is the situation. Let m greater than 3. This is the particular situation where we are talking about. Let m greater than or equal to 3. Then A is equal to the matrix whose first column is b2, second column is b3, and all other columns are 0. And because A is this one, column space of A is generated by these two vectors b2, b3, and they are linearly independent, is a proper subspace of R power m. Because m greater than or equal to 3 is a proper subspace of R power m. That means there exists b1 belongs to R power m, b1 not equal to 0, such that b1 does not belong to column space of A because it's a proper subspace. When b1 does not belong to column space of A, that is, the system Ax is equal to b1 has no solution. b1 does not belong to column space of A. Recall that earlier theorem. Ax is equal to b1 has no solution means this is the statement 1. So statement 1 is true. Thus, both statement 1 and statement 2 can be true. In what context? When m greater than or equal to 3 simultaneously. In this situation, that is why it can be true. It can be true simultaneously. Right. So that will give you the option 3 is true. So move to the next option. Option 4. If m is equal to 2, that means A is a 2 by 2 real matrix, then at least one of the statements 1 and 2 is false. So m is equal to 2, that means A is a real matrix of order 2. So we deal with two cases. Case 1 is when A is singular, where A is non-singular. Case 2 is when A is singular. Let us first of all consider case 1. Let capital A be non-singular. Then Ax is equal to B has a solution, and that too a unique solution, for all B belongs to R power m. How? Because A is non-singular, Ax is equal to B has a unique solution. What is that solution? X is equal to A inverse B. And it exists, it has a unique solution for each B, for all B power R power m. This shows the statement 1 is false. The statement 1 says there exists a B belongs to R power m, for which Ax is equal to B1 has no solution. But for each B, Ax is equal to B has a solution, and that too a unique solution. That is why the statement 1 is false. Since the dimension of R square is 2, yes, R power m we are talking about, m is equal to 2, so R square is equal to 2. So the dimension of R square is 2. There exist two linearly independent vectors b2, b3. Now Ax is equal to b2 and Ax is equal to b3 have solutions. Yes, we are in case 1. A is non-singular. X is equal to b2 has a unique solution. X is equal to A inverse b2. And A is non-singular. X is equal to b3 has a unique solution. X is equal to A inverse b3. So there exist two linearly independent vectors b2, b3 such that Ax is equal to b2 and X is equal to b3 have solutions. Thus, the statement 2 is true. So statement 1 is false. In this case, statement 2 is true. One of them is true. Right. Case 2. let A be singular. Then the statement 1 is true. Why? This is precisely what we have shown in option 2. When A is singular, the statement 1 is true. Okay. Assume that the statement 2 is true. That means there exist two non-zero linearly independent vectors b2, b3 belongs to R square such that Ax is equal to b2 and Ax is equal to b3 have solutions. This means b2, b3 belongs to the column space of A. Agreed? That means, and they are linearly independent. Therefore, the column rank of A is equal to 2 because we are in the case of M is equal to 2. Therefore, column rank is precisely equal to 2. That means rank of A is equal to 2. The rank of A is 2 means A is non-singular, which is a contradiction because in case 2 we are dealing with A is singular. This contradiction shows that the statement 2 is false. So, statement 1 is true and statement 2 is false. Agreed. One of them is true. So, this means the option 4 is true. That is when M is 2, then at least one of statement 1 and statement 2 is false. That's what we have proved. And the answer to this question is options 2, 3 and 4 are true. Option 1 is not true. So that is the detailed discussion of the solution of the problem, which is based on the solutions of linear systems from the section Linear Algebra. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.